I think we can start. My name is Michaela Taufer, and I'm a professor in electrical engineering and computer science at University of Tennessee, Knoxville. I am chairing this session, and I'm thrilled today to introduce Gustavo Alonso as the fourth keynote speaker of HPDC 2021. Gustavo is a professor in the Department of Computer Science at the ETH Zurich, where he is a member of the system group. He is also an ACM fellow and an IEEE fellow, and is a distinguished alumnus of the Department of Computer Science at the University of California, Santa Barbara. His research interests include data management, databases, distributed system, cloud computing, and hardware acceleration. Gustavo, we look forward to learning more about hardware specialization for distributed computing. Welcome.
All right, thank you very much for the kind introduction, and thanks for the opportunity to be here. I will, of course, like everybody else, I wish we could have been doing this in person, and we could all be in beautiful Stockholm. But unfortunately, we have to do it per video, so let's make the best of it. So I hope that I will be able to bring you a bit of a different perspective on distributed computing. I am quite familiar with high-performance computing, although I come from a different world. I come more from traditional data processing, databases, distributed computing for enterprise applications. But I think, like quite a few other people, I think that these worlds are slowly converging. And what I want to do as part of this talk is to give you at least a few thoughts on what is happening around the area of hardware specialization, something that these days is very close to our hearts in terms of research. So, and of course, let's try to make this interactive as it can possibly be made through a Zoom call. And if you have any questions or any comments, or you disagree with anything that I'm saying, please feel free to put questions or place your questions on the app, and then we will see them, and I'll be happy to discuss that as part of the talk. Okay. All right, so then let's get going. Let me just sort of give you a little bit my perspective on what is happening in terms of distributed computing these days. And what we are seeing is three important trends that I'm sure most of them will be familiar to you, but I think what is very important is the fact that we have these three trends at the same time. One of them, of course, is cloud computing. Cloud computing is not only something that is fancy and fashionable and everybody talks about it. Cloud computing really represents a major shift in the business model of the IT industry. And it brings something that is very, very important, is economies of scale. The fact that now you have a number of companies, definitely the hyperscalers, the 7 hyperscalers, but also a bunch of other minor cloud companies that are deploying computing at very high scales. And whenever you get these economies of scale, certain things happen that otherwise would not be possible. And one of the things that is happening is that, as you all know, and I'm not going to sort of show the standard slide showing that Moore's law has stopped and Denner's scaling is a problem, and multi-core and things like this, because everybody has seen these slides many, many times. But the results of those phenomena is the hardware evolution. Hardware is now evolving very, very, very quickly. And at least from my perspective as a researcher in academia, right, is evolving in spectacular ways. And this hardware evolution, of course, will have happened by itself because hardware has been evolving for the last decades with our cloud computing. But the fact that cloud computing is there is actually enabling some forms of new hardware that otherwise would not have been possible. And I will discuss a few examples of this in a second. And finally, the other trend that is very important is demanding workloads. Now, I'm talking to a high-performance computing audience, and of course, talking about demanding workloads to high-performance people sounds like a bit of a joke. However, in the wider world, if you want to, on enterprise computing, the fact that everybody is trying to apply machine learning to everything that moves, so to speak, and that everybody has very large recommending systems, and these systems need to operate almost at real time, and they need to operate on very large amounts of data, is creating an environment in terms of the applications, in terms of the service level agreements that need to be met, that it is very, very different from how things used to be. And as I said at the beginning, what is interesting is how these three things, or these three trends, are actually converging to influence how distributed processing is shaping in this century, and what it will be happening in the next years, which I think is going to be very, very interesting. And especially I'm looking at this from the academic perspective. If you are not aware of these trends and you don't pay attention to what is happening, especially on the way hardware is evolving, then in research, there is quite a bit of a good chance that you might actually be left behind, because if you are only working on software solutions, anything that actually takes advantage of the new hardware that is appearing is going to get ahead without actually much effort. And this is something that one needs to sort of pay attention to. So the talk, what I have done is organized it into three parts. First, I'm going to give you a few examples from industry, things that come mostly from cloud computing, but not only. I know that some of you will have heard about these examples, some of you will be familiar with them, but my experience talking to many people in different communities, I work not only on the databases, but also in distributed systems, also in the systems community. A lot of people, once more, especially in academia, are not entirely aware of all these developments. So I want to sort of use some of these developments as an example of what people are doing and why people are actually building these new type of systems. Then in the second part, I will explain a little bit about Ensian. Ensian is a research computer that we are building at ETH. And I'll explain you why we are building such a computer and how it looks like and what we intend to do with it. And then I will just briefly discuss some research directions that we have been pursuing that are sort of course, built on the two first parts of the talk in terms of how systems are evolving and this Ensian computer that we are building. So let me start with a few examples from industry, right? So now in distributed systems, distributed systems have always been an interesting setup. Many years ago, when I had to teach the class on distributed systems, I always told the students, look, distributed systems are very cool, but if you have a chance, you don't actually distribute a system, you centralize it as much as you can. Because if you have a centralized system, you have much more control, it's much easier to develop, it's much easier to instrument and understand what's going on. The moment that you start distributed things, then life becomes complicated. However, today, the world is distributed, and especially because we are moving to this type of cloud computing platform as the dominant platform in the cloud by design, is everything is a distributed system. Everything that is happening happens in a distributed form. Now, in a distributed system, data movement has always been a problem. And especially now that we are talking about big data and all this machine learning and data science and large scale data processing and so forth, this data movement is becoming an even bigger problem. Now, data movement is very well known. I mean, if you talk to architects, they will tell you, of course, we know this, right? We know that even within a processor, right, or within a computer, data movement is one of the biggest sources of energy consumption, right? And not only with the CPU, it's also within a computer. But now we have this at a much bigger scale. We have this across a data center. And in some cases, again, if you look a little bit at how Microsoft or Google or Amazon operate, this is actually happening across the world. You have regions, you have availability zones and things like this where data is actually being moved, in some cases, even across continents, right? So because we are no longer processing in a single computer and we are actually processing these large amounts of data, now it turns out that the data movement overheads that we are actually causing by this type of architecture are no longer acceptable. And the question is that what are people doing about these things? So let me start with an example. This is actually does not come from cloud computing, but I want to put it in there because it's an example that is very close to my heart. And it actually has the advantage talking to a high performance computing audience. Nobody will be offended. When I talk to my database friends, I always come up with this example and they get offended because it actually shows how stupid databases are. But actually, this is a very common problem in many systems. So in a database, as most of you will know, you actually use SQL to declaratively process data. And then you can write something like this: select a star from T being a table where the ID equals 3. And in essence, what this is saying is that go through this table and find out the tuple where the ID equals 3. Or if ID is not a key attribute, give me all the tuples where ID, whatever that attribute means, equals 3. And lacking anything else, the way this is going to be executed, this is a scan over the whole table, comparing or doing a predicate matching on this attribute and selecting the tuples where that attribute matches the constant that you have on the query. Okay. Now, what will happen is that in traditional databases, this whole table will read from memory. It will be brought all the way down to the CPU registers, and then you will throw away everything that you have read but one tuple, typically if the ID is just one key, all right? So you have a huge amount of data movement just to pick one tuple. And of course, as the data amounts that we have in databases, and today, for instance, it's not unusual to have tables that are 20 gigabytes, 30 gigabytes long, then, getting 20 gigabytes all the way to the CPU just to pick one tuple that maybe is a couple hundred bytes long doesn't sound like the most intelligent thing to do. Okay. So what can you do about this? Well, Oracle came up as part of one of the Spark processors a few years ago with an interesting idea. What they did is that if you look at the picture on the top part of the slide, you see the standard architecture with these are several sockets with different cores, right? I mean, 4 cores in each one of those sockets. And there is an L1 cache, an L2 cache, L3 cache. There is an on-chip network. There is the memory, right? And in between the memory, and this is the interesting thing, in between the memory and the on-chip network, there are accelerators. What do these accelerators do? That's the figure that you have on the lower part of the slide. These accelerators, what they do is they actually process the data as it streams from the memory to the caches. And among other things, they do things not only related to databases, they also do things that have to do, for instance, with software engineering. They do pointer checking and then make sure that you're not accessing things that you're not supposed to access. They check null pointers and things like this. They also have encryption and some security. But from the perspective of databases, what they do is that this filtering, right, of having to read a whole table just to pick up one tuple no longer happens at the registers of the CPU. Now it happens on these accelerators as the data streams from memory to the processors. And that has the big advantage that you're actually removing a huge amount of problems in terms of computing. You're no longer polluting the caches. You're actually not creating bottlenecks in memory access. You're not actually collapsing the data buses by moving so much data, right? And so forth. So this is really a great idea. And actually gives you, I think, a very good intuition of the amount of unnecessary data movement that we have in many systems. I'm just going to use databases because I know them quite well as an example for many of the things that I'm going to present, but this is common in many, many systems, right? And this type of processor gives you an idea of how companies are starting to sort of react to the fact that this data movement is problematic. Okay. And of course, you will have heard about some of the developments around these ideas, like for instance, in memory data processing, this is where you actually turn the memory into an active component, where you have some logic to enable basic data processing. What happens is that in-memory data processing tends to be very limited. You can only do certain operations, right? You cannot have a full processor in the memory, but that already allows you to do some operations without having to take the data out. Another version of this is near memory processing, like the example that I have just presented, where there is a processor that is located close to memory, close to the data, in order to process it as it actually flows out and so forth. Right? So these are interesting developments that are happening and that we are seeing more and more of them. Let me actually take this idea and now extend it to a data center. So imagine that we want to run exactly the same query, but we want to run it in Amazon. Okay. And for those of you who are not familiar, Amazon has these very, very large systems for what are called data lakes or data warehouses, where you actually process terabytes of data, huge amounts of data. And what happens in the cloud is that you separate computing from storage. So storage is a layer that is running on certain computers where the data is stored, and the computation actually happens on different computers. So now the reading of the data is not coming from memory, reading of the data is actually coming from a remote storage system, and you're actually involved in the network. And exactly what I said that happens on a processor happens at the level of the cloud. You will read the whole table from the storage, you will bring it into your machine, you will put it in memory, you will read it all the way to the CPU registers, just to throw everything away by one tuple. right? Which obviously, again, doesn't make any sense, and now becomes an even more or an even larger problem, because now you are not only sort of creating problems within your computer, you're now creating problems within the cluster or within the data center, because you're accessing the storage, you're going through the network, you're accessing the network card that you are sharing with other VMs and things like this, right? Okay. So now this is where sometimes people become a bit skeptical and they say, okay, you know, what can you do about this? I mean, this is inherent on the nature of the problem, because you have a lot of data and you cannot keep all the data in main memory. So this is always going to happen. And this is correct, but this is where hardware specialization is kicking in. And let me just show you this example of something that Amazon has actually very recently put out that is called Aqua. Aqua is an intermediate caching layer that sits between Amazon Redshift. Amazon Redshift is a large, let's call it a large database, data warehouse that Amazon offers. This is for processing very, very large amounts of data. And this caching layer sits between the computing nodes, that's the red layer that you see in the figure, and the storage that Amazon uses, that is S3, that is the green layer that you see below, okay? And of course, Amazon S3 is durable storage. It offers different forms of storage and so forth, but for obvious reasons in terms of cost and efficiency, right, this doesn't tend to be the fastest storage that you have. So if you imagine this problem that every time you want to run one of the queries, you want to read all the data from storage, then you see the overhead that this causes. And you can say, well, but what I do is that I don't read the data every time. What I do is that I read the data and I keep it in main memory on a compute node. But if you know about the business model of Amazon, keeping a compute node up with enough memory to keep your data in memory is also expensive, right? So you, in essence, start getting into an interesting trade-off. So what Amazon has done is that it actually has introduced, again, this caching layer that is, in essence, are SSDs, which are much faster in terms of giving you access to the data than S3 in general. And what is interesting is that on these SSDs are connected to an analytics processor, as they call it. This analytics processor is an actual FPGA. And what this FPGA does is something very similar to what Oracle is doing on that processor. What that FPGA does is that you can actually push down a lot of operations on the data directly onto this intermediate storage node. So of course, the first time that you want to access the data, you need to sort of go to S3, but then the data is on this Aqua layer. And next time you want to access the data, you're not only going to get it from that layer, which is faster, but you're also going to be able to push part of your query down to the storage layer. And the storage layer is going to be able to do things like filtering, selection, projection. It actually does things like predicates, which is actually based on strings, regular expression matching and things like this. So this actually gets quite a bit sophisticated, right? And again, the whole point is that you cannot afford to be moving a couple of terabytes of data all the way to the compute nodes just to actually get rid of 90% of it, because you're interested only on 10% of that data. Okay. So what you're seeing here is a very good example of this trend, that now compute is no longer happening on the compute nodes, but compute is starting to happen at essentially all layers of the system. Right? Now, I don't have it on the slide, but some of you might be aware that, for instance, S3 itself already supports processing. So S3 has something that is called S3 Select, where you can actually push down select operations for certain type of data files. And in essence, that's the same thing. Instead of actually giving you the whole data file, it first actually selects parts of the file, and then it gives you only the parts of the file that you are actually interested, right? And even more, as part of serverless, they are now offering an interface where you can actually have user-defined functions that are attached to the storage. And you can actually, whenever you're accessing the data, you run your user-defined function, and the user-defined function does the filtering for you. Okay, so you see that now, whenever we talk about computing, we're no longer talking about computing in one compute node, but now we have a whole hierarchy of computing steps that are distributed across the whole system. Okay. Now, The developments that come out of this are, of course, in storage data processing. You're going to see this more and more and more. Storage will no longer be a passive component. It's going to become an active component that can do quite a lot of things. We're going to see a very heavy use of caching layers. And again, just in the interest of time, I'm not going to go into this direction, but of course, we have non-volatile memory that is being used to expand some of these systems, right? I mean, so you will have L1, L2, L3, DRAM, non-volatile memory, then you will have this caching layer that I have introduced, and then behind that, you will have the storage in the cloud and so forth, right? I mean, so you're going to have very deep memory hierarchies, and those are starting to happen. And in each one of these layers of the memory hierarchy, it is likely that you're going to have processing attached, okay? All right, now in the interest of time, let me sort of now show you another example. And this is one that I think a lot of people know because Microsoft has actually been very open about it. They have written quite a few papers and given a lot of talks in many different venues. And this is the Catapult project, right? And in the Catapult project, what is interesting about it, well, there are many interesting things about the Catapult project, but what is interesting about it is that although they have quite a few papers where they show that they can accelerate applications and so forth, what is interesting about it is that the main usage that they have for it, at least as far as I am aware, is actually making the whole computing platform more efficient, not necessarily a particular application being faster. So what is the problem in the cloud? The problem in the cloud is that if you are a cloud provider, you want to rent machines to people, and the way you rent these machines is by packing as many users as you possibly can inside VMs, and you want to put as many VMs as you can in a computer, because that's how you actually make money. However, in order to provide isolation, in order to provide access to resources and so forth, you need to have network virtualization, and these network virtualization functions are actually quite expensive. So Microsoft, for instance, has said that for their typical VMs and the typical deployments that they have in the cloud, within one computer, they might actually have to devote up to 8 cores to implement the network virtualization functions. So that means that you're losing a huge part of the real estate of that computer that you're supposed to be renting to people in order to make money. You're losing it just to support the infrastructure. So what they did is they actually moved that infrastructure to a smart NIC that is based on an FPGA, and they have had different versions of these in different ways in which they are connected and so forth. And if you are not familiar about it, especially if you come from HPC, you will recognize many of these connection patterns and topologies and all those sort of things that they have been exploring, because they have, they are quite related to what high-performance computing has been doing for quite a while. But the latest version of what Microsoft has on this is now a smart NIC that has an ASIC that implements the network protocol, and then it has an FPGA where they put the smarts for the network. They not only put the smarts for the network, they have a bunch of papers where they have this brainwave project where they actually do a lot of machine learning. They also support key value stores where they are doing RDMA acceleration on the FPGA. So they actually have been publishing a number of papers where they actually show all the great things that they can do with this. Right? But once more, what is the consequences of this idea is that now it is not only the case that we are having these storage layers that are becoming active, is that now the network itself is becoming active. And again, I know that active networks is a very loaded term that was used in the past, but when I said they are becoming active, I refer to we're having a smart NICs where we're actually pushing processing of the data to those smart NICs. Because if the data has to move anyway, the storage is remote, I need to send it through the network, I might as well do something useful on that data as it goes through the network. So this notion of in-network data processing is also starting to appear, not only as a way to accelerate applications, but also to delegate expensive CPU overheads into these smart NICs, so that the CPU can actually be used for something actually more useful, right, if you want. Okay, very good. Now, what are we doing about this? I hope that I have given you a number of examples, and literally we could spend another 2 hours keep talking about examples and things that are happening, because there are really, really very many of them. Now, the question is that if you are in academia, like I am, and you see all these great developments. The question is, what do I do? Because, of course, I don't have access to some of these deployments. I mean, Microsoft, for instance, has not made Catapult available to end users. I understand that they have it available for some privileged users, that they are trying to sort of put applications in there, but I cannot just go and run these FPGAs or these SmartNICs and try to do something on them, right? Also, although they have published a lot of things, right? I mean, a lot of the hardware stack and the software stack that is in there is not necessarily publicly available. But you immediately realize if you continue building systems, and this is what we do for a living at ETH, and you continue building systems, ignoring the fact that in reality, people are moving a lot of these functions to hardware, you are going to lose. I mean, you are not going to be able to build systems that are competitive because you are building them on platforms that by definition are going to be much slower than what is used out there. So we realized this quite a while ago at ETH as part of the systems group, right? I mean, where, as I said, we try to build systems in general. And we decided, okay, these are challenging times and we need to do something about it. And in spite of the fact that all of us come more from the software side, we decided we need to do something new. Otherwise, we are going to be in a place that we don't want to be. Okay. But the problem that we face is that it is very difficult to explore these possibilities, right? You can always say, okay, I want to focus on FPGA development. And for instance, in my group, now half of my group are electrical engineers, and we are doing development on FPGAs. But FPGAs are just a very small part of these developments, right? I mean, you're having a storage, you're having more processors, you're having a very interesting combination of architectures and all those sort of things, okay? So we decided that we were going to try to build our own accelerator. We are going to try to build our own computer, not something intended to be commercially viable, but trying to build something that gives us a flexible platform for actually doing research, exploring how hardware acceleration and these type of systems that we are seeing appearing everywhere, how they could actually look like, okay? And this is Ancient. So Ancient is a project that has been going on for already a few years. In principle, if you look at it, it's just a dual socket system. On one socket, we have server-grade ARM multi-core chip with 48 cores, ThunderX, with 120 gigabytes of memory. And on the other socket, we have a large FPGAs, Xilinx UltraScale. And here is where some of the novelties are, right? I mean, so the FPGA actually has 512 gigabytes of memory. This is a very large amount of memory attached to the FPGA. Why? Because we wanted to, typically if you get an FPGA commercially, they have now, 8, maybe 16 gigabytes of memory, sometimes 32, but really not much more than that. And that actually limits the type of applications that you can put in there. And we wanted to explore what happens if I have an accelerator that in fact has half a terabyte of memory, where I can put a very large application directly on the accelerator. I don't need to be moving data back and forth between the host and the accelerator. Now I'm running the whole application on the accelerator. What happens when that is the case? So that's one of the interesting innovations that we have in there. Another interesting aspect is that the FPGA and the cores, the CPU, is cache coherent, which again is not a novelty. There are already FPGAs and accelerators that are cache coherent. What is novel here is that the implementation of the cache coherency protocol, what we call the Ancient coherent interface, is actually something that we have developed, and it will be open source. That means that the application will be able to manipulate the cache coherency traffic, and we actually be able to access the cache coherency protocol at different levels, so that you no longer have to live with whatever the hardware vendor provides in terms of cache coherency, but you can actually try to sort of adapt the cache coherency protocol to whatever the application wants to do. And there we have a lot of very interesting ideas of what can be done. One of them, of course, is connecting the cache coherency protocol to the network. The other thing that this FPGA card has is 400 gigabit ports for the network that we can all connect to a switch. And we can actually put the logic in there that actually connects the cache coherency protocol to the network, and then see if we can actually start implementing distributed systems that give you a little bit more than just traditional shared memory, but where you can actually exploit having access to this cache coherency protocol to actually provide more interesting things than what you typically have. Okay. So this is a system that, as I said, we have been building for the last years. Now I'm happy to report that, in fact, maybe 6 months from now, it will have been a bit more difficult to give this talk. Now I'm happy to say that, in fact, this exists after some problems that we encountered in developing the hardware. What you see on the big picture right on the right is one of the boards that was developed. That is not still on a case. But for testing, but this is what we have been using to develop all the software, operating system, and all the things that need to turn this into a normal computer. And what you see on the left, these are actually several of these boards turned into normal computers already in the cases to be able to put them on a cluster, right? I mean, so very soon, in literally a matter of weeks, we're going to have a cluster of these things up and running. And starting to develop applications on top of those things. Now, what is interesting about it, and I think in the context of a conference like this one, might be of interest to a big part of the audience, is that our intention is to make everything open source, both the hardware and the software. And so if you don't want to develop based on what we have, your own hardware and so forth, you want to use what we have. The idea is also to make these machines available remotely to other researchers to be able to work with them. And we're still trying to figure out exactly how to do this, but probably we'll also try to have a scheme where if you want to buy one of them, you will be able to buy one of these machines, or maybe more than one machine if you want to build a cluster, so that you can actually go and do your own research or do your own development on them and so forth. Right? And the other thing that we're doing, of course, is that we are trying to create an ecosystem of open source tools and systems that will work on this platform. And this is very important because anything that has to do with hardware acceleration, everything is very, very proprietary, right? I mean, so it belongs to the vendors, and there is very little thing that you can do in there in terms of building your own system. So as I already mentioned, we want to sort of make the cache coherency layer on the FPGA. We want to make that open source. We have a full implementation of an RDMA stack at 100G on the FPGA as well, that combined with the cache coherency protocol, for instance, allows you to RDMA directly to the cache, to the L1 cache of the cores, right? Which enables interesting applications. We also have a 100G TCP/IP stack, which again, both stacks are open source, so you can modify, you can change them, you can actually extend them in whatever way you want. We have an operating system on the FPGA. I'll explain it, I'll present it briefly in a second, right? I mean, and so forth. And of course, we are continuing developing many things in here. And so if you are interested, I'm happy to talk to anybody or just contact us, right? I mean, and join the party. This is an open project, and as many people as, and we are welcome as many people as they want to contribute and collaborate in this project. Now, let me actually just wrap up this presentation with a little bit of a few ideas, right? I mean, of what can you do with a platform like this one. These are ideas that we have been pursuing already for quite some time, but once we have a platform like NCL available, all of a sudden we can really start building very complex systems that otherwise we would not be able to build. And we'll actually be able to come up with something that is really competitive with what is out there and provided by the cloud providers. So let me start with something that has to do with directly with distributed computing and related to RDMA, right? I mean, that's something that everybody in the audience will be able to relate to. And this is SmartNICs with 100 gigabit networking, right? I mean, now, I know that, of course, this type of SmartNICs exist. Mellanox has some of those. People have been talking about this type of SmartNICs and so forth. However, until now, the type of applications that people have put in there have been limited. Now, imagine that you have access to a type of FPGA like the one that I have presented that has half a terabyte of memory attached to the FPGA, and you can actually directly RDMA to it or from it. Okay. What can you do? And not only this, you can also access the memory of the host if you want, right? So one of the things that we implemented, and this is a paper that we published last year, one of the things that we have implemented is that in distributed computing, typically you want to access a data structure that is remote. But some of these data structures, you need to navigate the data structure. For instance, if you have an index, or you have a linked list, or you have a tree, or you have a hash table, you have to navigate the data structure. And through RDMA, this becomes complicated. Either you are using two-sided RDMA, and then you are consuming CPU cycles on the other side. And if you want to use one-sided RDMA, then you have the problem that you need to go back and forth in order to navigate the data structure. So with the platform that we have developed, we actually use one-sided RDMA, and we use the SmartNIC to actually traverse data structures. Okay, and the figure that you see here, it actually compares Strom, that is our SmartNIC implemented on an FPGA. It actually compares it with a commercial card, and you see that we have competitive performance. We are really in the ballpark, right? I mean, sometimes faster, sometimes it's slower, but it is something that is reasonably competitive. And then what we can do with it is actually, for instance, that's the figure that you see now on the slide. We can actually do things like traversing a remote linked list. So you want to access something on a linked list, you're looking for a particular item. And if you are doing this with one-sided message, then you actually have to go back and forth, right, in order to traverse the list. But now we're actually using the SmartNIC to say, I want to read this element, and it's the SmartNIC, the remote SmartNIC, that actually would do the traversal, the list traversal, and then send you the data that you need, right? And what you see in there is what is the cost of doing this for different sizes of the lists using traditional RDMA, again with a commercial NIC, or using our system where the traversal happens on the remote machine. But very important, the traversal happens organized by the SmartNIC and not by the CPU. You're not consuming CPU cycles on the remote machine. Okay. And we can do this not only with linked list, we can also do it, for instance, in this particular case, this is a hash table lookup. As you know, in hash tables, sometimes you have collisions, right? I mean, and this actually creates all sorts of problems when you try to do remotely. And what we can do is very easily have the SmartNIC take care of these collisions and so forth, right? I mean, so you just one day access the item, and then it is actually the traversal is being done, or the hash table is being done by the SmartNIC remotely. And like before, you get a significant performance improvement. Now, these are relatively small examples, which are not doing anything sophisticated, but we can actually put relatively complex processing into the SmartNIC. So one of the things that happens when you implement large-scale key-value stores is that typically these key-value stores have a bit of a problem with consistency. And then the way you actually make sure that whenever you are reading an item, you're reading a value that is consistent is that you read the value, and then you check the cyclic redundancy code of that value. And if it is correct, then you know that you have read something consistent. But if it is not correct, then you have to read it again, because that meant that you were reading while somebody was modifying it. Okay. Now, again, if you try to do this with a one-sided RDMA, then you have the problem that you bring the value all the way back, and then you look at it and you say, okay, this is actually the wrong value because the CRC does not match, so I have to go and read it again. So one of the things that we do again with this SmartNIC is that the SmartNIC will read the value, will check the CRC. If it matches, sends it to you. If it doesn't match, it goes and reads again, and it continues reading or keeps reading until it actually reads the correct one, and it matches, and it actually sends it to you. So these are just relatively simple examples of what can be done, but realize that we can extend this in arbitrary ways. If you think of the examples that I have given you before of Amazon Aqua, or this Oracle processor that actually push filtering and all those sort of things, right? I mean, close to the data, we can actually do something similar. Now, of course, one of the problems of using these accelerators is that typically you do not have multiple cores, you do not have many threads. In an FPGA, typically you have one region that you can actually program. So one of the things that we have done is that we have developed Coyote, which is, just for lack of a better name, is an operating system for an FPGA. And one of the things that it provides is actually the ability to do just, again, it's not multi-threading, but for lack of a better name, let's just call it multi-threading. It allows you to have different threads running different applications inside one FPGA, and also sharing an RDMA or a TCP/IP network stack and all those sort of things, right? So we had recently a paper describing how this works, but so in a nutshell, what this allows you to do is allows you to put several applications running on the same FPGA. And then once you have this, one of the things that we have been doing on the last year together with HPE, and this is just also this actually one of the applications that we have in mind is high performance computing, is smart disaggregated memory. We can actually take a chunk of memory, we can put it on the network with an FPGA, and then we can actually put all these data processing capabilities directly on the FPGA. So in essence, we can actually do what the examples that I have mentioned before that Oracle is doing within a processor, or that Amazon is doing in this intermediate caching layer. Now we can do it with DRAM. In the future, we want to do it as well with non-volatile memory, but right now we are doing it with DRAM. And we can actually attach large pools of memory directly on the network, be able to access them through RDMA, and be able to push down processing all the way to memory. And in the context of the cloud, on the context of large-scale distributed computing, this is very interesting because it allows you to grow the amount of data that you have in memory, as opposed to having to build machines or add machines to your system in order to have more memory capacity. Okay. Now, this is actually based on the example that we have built with this is based on databases. But in essence, what you need to sort of think about this is that databases, what they give you is a query plan, and then the query plan is a number of operators that are captured as a tree. And then what we do is out of this query plan, we take all the operators that are on the lower parts of this query tree. We no longer execute them on the compute node. Those are the operators that we are pushing all the way to the disaggregated memory, and these are executed on the disaggregated memory. Okay. So this is what you see here on the figure on the right. This is how this is actually implemented. So we have RDMA, and with again 100 gigabit. You have dynamic regions with operators, and then there is a memory management unit that actually virtualizes all the channels that you have in there, and actually gives you access to all the data that you have in there. And we can actually do a lot of things on this disaggregated memory. We can do encryption and decryption. We can do projection, so we can actually read tuples or rows of data and select data from there. We can do selection. We can do regular expressions, regular expression matching. We can do a string search. We can do group bys. We can do aggregation. And of course, we can actually pack, reorganize the data, encrypt it again, compress it, and all those sort of things, right? So all those things can be done directly on the disaggregated memory. And we think that this is really the way to implement disaggregated memory, because otherwise, disaggregated memory gives you a little bit better latency that you're going to have out of storage, but you're still moving a lot of data back and forth. And if you look at what is happening with storage, that is becoming smart storage, disaggregated memory, if you're going to ever going to make it competitive, has to become smart. And this is one way in which we think that this can be done, and can be done very efficiently. Okay. All right. So I just want to sort of finish here. I have a number of other examples that I'm not going to get into them into detail. One of the things that I want to mention is that this type of accelerators, not only FPGAs, but other type of things that you can put in there, really allow you to do things that on CPUs are actually quite expensive. So if you are trying to process streams, for instance, on CPUs, you have the problem that the stream comes to the network, needs to be put in memory, then it goes to the registers and so forth. You waste a huge amount of time. While if you actually do it on the network, you can actually process the stream directly as it comes from the network packets. And also, CPUs are based on having threads and so forth, which are not very good at processing shared data. While if you have this type of accelerators, we can actually have pipeline parallelism. And what I show here on the slide, and again, I don't want to get into many details. If you're interested, we can discuss it as part of the questions. Here, what we have been able to show is that we can actually run several sketching algorithms. Sketch algorithms are algorithms that are run on streams to give you information about, for instance, the cardinality, the frequency, the second frequency moment of a stream, and so forth, that are used for in machine learning and also to characterize these streams. And each one of those things is expensive. And we can actually show that we can actually put them on these accelerators, and we can actually do all of them together with no additional cost. So you can actually, it is not only that you are moving only computing, you can actually do a type of computing that on the CPU will be very, very expensive. Okay. All right. So now, in the interest of time, and just to make sure that we have some time, I see one question on the app. I'll get to it once I finish this. Let me just finish this in a second. I'll go to the questions. So I think hardware acceleration, the main message is that hardware acceleration and specialization are here to stay. Even in spite of the fact that many software people don't like this, because it actually changes the game in a significant way. I think until we get a completely new generation of processors, I think hardware acceleration and this type of architectures that I have been presenting are going to be dominating the computer infrastructure for years to come, probably for decades to come. Okay, and this bottleneck and these inefficiencies of moving large amounts of data back and forth, right, are only going to become worse. So this is actually an additional motivation, right, for having this type of fancy architectures where there is processing all over the place, because otherwise you cannot actually deal with the overheads that data movement actually have. Okay, so it is an interesting time. This is not just about hardware, because the hardware is there, but now we actually need to build the software that they can take advantage of this. Software is much more difficult to build than hardware. Even in spite of the hardware is more difficult. Software has typically a much larger lifetime, often in the decades, right? I mean, so it's much more difficult to evolve and so forth. But now we're at the stage where we really need to sort of start thinking about building software systems in a completely different way in order to take advantage and be able to cope with what opportunities the hardware is offering. Okay, so I'll finish here. I'll just leave you the slide thanking everybody in my group, my PhD students, postdocs, also many former students and postdocs, because this has been a research program going on for quite some time, and especially in the systems group, the ancient team, that is all the people who have been fighting building this hardware that we have built. And with this, thank you very much. And I'm happy, I think we have time. I'm happy to answer questions, right?
Indeed, we have. Thank you so much, Gustavo, for this wonderful talk and so many insights in the direction of hardware development and integration. We have indeed a couple of questions. I start with one that is posted. I remind you all that if you have questions, please add that into our interface. And the first question is about how does the accelerator interact with a file system?
Right. So just to sort of make sure that I understand the question, right? I mean, so the accelerator in the cloud will interact with the file system in the same way that a compute node will interact with the file system, because typically the file system is on the network. So you're actually just invoking whatever interface the file system is giving you from the point of view of the accelerator. So that doesn't change, right? If I understand your question correctly.
And if the person who asked the question want to clarify, please feel free to add additional comments. I have a question about the overall vision that you gave us of industry. It is always the fact that industry is 3 steps in front of academia, and sometimes they developed their own solution in a silos, and then they put that as a product. It looks like for some of us that the financial challenge and the human capacity challenge discourage us to even compete. So, but on this, at the same time, from your talk, you and your group has been able to embrace innovation, develop systems, and sort of break this negativity. I would like to have a little bit of comment about what should we do as academic to have the same or similar pace as industry and embrace new challenges, despite the fact that industry has such a big financial support that in academia is not possible.
Right. So I think this is a very important point. I mean, I think we have always been a little bit in this situation because industry at the end, produces many of the things that then we have to use, right? I mean, and then you're stuck with them. So there are two problems here. One of them is that, as you said, typically in academia, you do not have the resources to be producing new processors or new computers every 2 weeks because it just costs too much money and too much effort. The way to actually tackle this problem is collaboration, is building larger groups. This is what we have done within ETH, but we are also very quickly expanding around MCN to other groups at other universities and other researchers who are interested in different aspects of MCN and so forth, right? I mean, and we hope that around this we will be able to build not only a community, but also a whole ecosystem of software applications, examples, and things like this. And this is important not only in order to compete with industry if you want to, but also to, let me put it in this way, to keep industry honest, right? Because I mean, right now we have many scientific conferences, have many papers from industry where they go and claim many things, and nobody has a way to actually check that in fact the numbers that they're giving you or the claims that they are making are correct, because you don't have access to these systems. You cannot replicate those numbers. They are based on insights that they gain from data that you don't have access to, right, and so forth, right? And companies are not innocent, right? I mean, so they tell you what they want to tell you, and whatever they don't want to tell you, they don't tell you. So the fact that having more of these platforms, right, available for research will actually allows us to get a much better perspective, a more neutral perspective on technology. That's one aspect. The other aspect, which is also very important, is that it is not entirely true that industry knows always what they're doing. So especially in this world of hardware evolution, right? I mean, of course, they are putting out products and things like this, but it's not entirely not always the case that what they do makes sense or actually works. For instance, the Microsoft Catapult project, I think, is fantastic because they have been very open. They have published a lot of papers, but if you read the papers, right, when they started with the first paper, which I think it was around 2014, right, they themselves are very honest. They say, we put this system out and we realized this doesn't work. In a cloud, you cannot deploy something like this. It will be too expensive. It will not solve the problems that we have and so forth. So this is why we have a second version. And 2 years later, they came up with a second version where they actually modified the architecture and they say, this is actually better. And now they have a third version, right, out there, which works even better, right? I mean, so you see that a lot of these ideas, right, I mean, or these systems that are being put out, they come within a company. Companies have a very well-defined perspective on these problems, and having more people outside these companies working on these problems will make the technology better by making it more generic, applied to other applications, or actually try to understand better, not just buy what these companies tell you, because you don't have access to these systems. Okay?
Yeah, there are a couple of questions I want to touch because they are quite relevant. The first one is about if you can say a little bit more about the effects of hardware specialization on programming models in your context.
Yes, this has been a fight that I have had with all my programming languages and software engineering friends for a long time. So this is definitely a challenge, right? I mean, so once you have this type of architectures, right? I mean, the question is that what is a program? And this has always happened with distributed systems, right? A distributed system is the whole thing one program, or is a connection, or is a collection of programs that are exchanging messages and interacting with each other, right? I mean, and in high performance computing, you know this very well, right? I mean, is a weather simulation, is that a single application? Probably you will actually treat it as a single application, right? I mean, but there are many other distributed applications where you will say, you know, no, this is not a single application. This is a stack of applications that are exchanging data and are doing quite different things, right? So especially in the cloud, I think the way these applications are being built, right? I mean, in terms of programming models, this is actually forcing people to change the way systems are being built, just necessarily. Now, I don't have a magic bullet. I cannot tell you this is the programming language for the cloud, but I think this is actually changing, right? I think, for instance, one of the things that, and this is also something that I always tell my students, a few years ago in computer science, especially the programming language people, they were all fighting about which one is the best programming language, right? I mean, people will claim this programming language is better than the other and things like this. This discussion has stopped. And I think this discussion has stopped and no longer make any sense, because this type of very heterogeneous architectures and this type of like very distributed computing that we have implies that you're going to have a lot of very different languages for different parts of the systems. So I'm a little bit less concerned about the programming model. I'm a bit more concerned about how do you architect all these different systems, because I think every part of the system is going to be programmed in a different programming language. I think I'm seeing a very big push towards domain-specific languages, right? I think we're going to see many more of those. But then the question is, how do you build large systems that actually have all these different components programmed in using different languages, right? So that is a very big challenge.
I want to cover the last question because we're at the end of the session. It is about reconfigurable architecture that's been around for a while. So why is the time of reconfigurable architecture in HPC now? What is different that 5 years ago, 10 years ago?
No, this is a very good question. And I have been working with FPGAs for about now 10, 12 years, right? I mean, and 12 years ago, I would have told you, well, I'm doing this as part of research. I will not recommend anybody to try this. I'm just exploring the architecture. I think what has changed is not so much on the HPC side or the cloud computing side. I think what has changed is, as I said, is the pressure, is the applications that no longer, you can no longer meet the service level agreements, right? Or the demands of these applications using traditional CPUs. That is one aspect. And the other one is that the way in which this reconfigurable computing, the way FPGAs have been evolving, right, they are today fundamentally different from how they were 10 years ago. So we work very close both with Intel and with Xilinx, right? And if you look, for instance, in the case of Xilinx at the newest Alveo cards or the new Versal card that they are putting out, right? I mean, so the new Versal card, that's in essence is a computer in a box, right? I mean, it has ARM cores, it has AI cores, it has reconfigurable computing, it has networking, it has floating point units. So it's actually far more than just an FPGA. And this is actually, I think, the hardware is actually changing, right?
Thank you, Gustavo. And I want to thank also all the attendees for their questions. This has been quite an enlightening talk, and I think we will have the entire conference and the several breakout sessions to continue the discussion. Thank you again, Gustavo, for presenting all this idea to us. And I want to wish everybody a fantastic conference.
All right, thanks to you, thanks to everybody, and you know where we are. If you're interested in these topics, if you're interested in collaborating or you're interested in Ancient, just please contact us. I'll be more than happy to talk to everybody. Right, bye-bye.